Right. So what we'd like to do now is take a look at a totally different idea, which is the idea of material that is dissolved in a liquid or solution. And the idea is that when you have a pure substance, there's only one kind of that material that is present inside it. And as you see here, this is a pure form of a molecule, which is propane. So do notice you can have multiple types of atoms present, but they exist as a molecule, and only that one molecule is present. Now, a mixture contains one or more kinds of substances. And here you have water mixing with what looks like to be a propane molecule, but you have multiple types of molecules present to create a mixture. Now, once you have a mixture going, there's two subgroups within it. Homogeneous is uniform in appearance. For example, when you have a cup of coffee or a cup of tea, there's multiple types of material in there, but they all exist as one type or uniform appearing material throughout it. So here you see a mixture which is a homogeneous type, and the other kind is a heterogeneous mixture that is different most commonly in more than one phase. You can have, for example, ocean water that has a little bit of sand in it. That's a heterogeneous mixture. The sand is a solid, and the rest of the water and salt and whatnot is dissolved in a different phase. We can look at this in terms of a chart. We work down your way through, is it a pure substance, if it's a mixture, if pure, does it exist in its pure elemental form like helium, or is in fact it a compound which is a molecule, but there's only that one kind of molecule present. Then you take a look at the heterogeneous, which is the not uniform throughout, like wet sand that we referred to. And of course, tea and sugar is a mixture of several materials, but it's homogeneous throughout. So matter will fit into those four major categories: in elemental form, compound, heterogeneous mixture, and then homogeneous mixture. Now we want to take a look in this unit at solutions. And solutions are homogeneous. It belongs to the category of the homogeneous. Two different types of materials are intermingling with each other at the molecular level. Now, when you have a solution, there are two parts to it. These are very important terms to keep in mind. The first item is referred to as the solvent, and it is the one that is in greater quantity. And then there is the solute, which is that which is dissolved or in it or has lesser quantity. We can think of making a sugar water solution where the water is the solvent and dissolved into it is the sugar, which is the solute. Now, once you have added the material like sugar to the water, the sugar goes through a dissolving process. And how well a material dissolves in the liquid is referred to the solubility. And the ability to dissolve in a liquid environment is not the same for everything. If you take cinnamon, for example, and add cinnamon to water, it doesn't dissolve hardly at all. In fact, it tends to float on the surface, whereas things like salt or sugar dissolve very, very well. And so this ability to dissolve into a given liquid is referred to as the solubility. Once you have dissolved something into water specifically, we refer to as an aqueous solution. So if you dissolve something in oil, you would not refer to it as aqueous. Instead, it's only material that's dissolved in the water that is considered aqueous solution. Polarity. Now, polarity is going to be an important idea, and we have not touched upon this yet in detail. That is the next unit coming up. But we do have to have some awareness about what polarity is, because it influences solubility. If you take two atoms and bond them together, in this case you have hydrogen on the left and you have fluorine on the right. Now it turns out that the nucleus of atoms have an ability to attract electrons. It's part of the positive aspect of the nucleus. But what happens is, in this diagram, a hydrogen atom does not attract electrons as well as the fluorine atoms. And the result is that when the two form a bond, the fluorine atom will exert a greater pull on the electrons that make up the entire molecule, not just the ones that are involved with the hydrogen and fluorine linkage, but all the electrons that make up the cloud around the entire molecule are influenced by the fluorine. One might imagine it from a gravity standpoint as the sun exerts a great gravitational influence on the other planets. Fluorine exerts a very great attraction to the electrons everywhere, greater than that of hydrogen. And the result is the electrons tend to hang out around the fluorine atom. And because of that, that's a more electron or negatively rich region, and the region around the hydrogen is poor. And that actually creates a slight charge around the two, with fluorine having a greater negative charge and the hydrogen having a greater positive charge because there are less electrons there. We symbolize this by having that unusual looking diagram or symbol which represents polarity, and you'll notice that the fluorine has the polar negative label, and then the other side is the polar positive. Now these are not ions. You don't have a complete loss of electrons. Instead, it's a concentration of the electrons on one side or the other. And what the arrow is saying, it gives you the direction that the negative polarity points to. And that's known as the polar direction. Now the reason why this is important is it's a very it's an influence it's a property that influences the ability to dissolve things. So these are referred to as permanent dipole moments, and it has a big influence from the standpoint of solutions. So there's an unequal charge distribution, and the big item here is water is extremely polar. So what this is you'll notice you have the oxygen and you have two hydrogens. That's the water molecule. But you'll notice that because of the really strong attraction that the oxygen nucleus, the oxygen atom nucleus exerts, it pulls electrons its way. And therefore the oxygen side of the molecule is polar negative because it can concentrate those electrons. The hydrogens, they don't have nearly the pulling power, if you will, of electrons, and so they have a more exposed nucleus, and therefore those two regions are polar positive. So water, the molecule water, is enormously polar in that it has an unequal distribution of charges. Now what happens is polar will attract other polar molecules or other charged molecules. The nonpolar, which we have not shown you right now, the nonpolar are attracted to other nonpolar, and therefore not attracted to other polars. Therefore, in water, ionic compounds, meaning those that tend to form plus or minus ions, will dissolve very, very well in water. Covalent bonds remain as complete molecules when they're dissolved in water. Now, you have two examples here. You have the NaCl salt, and when it dissolves in the water, then it dissolves because Na loses its electron to become a positive ion, and the Cl gains that electron to become a negative. You have an ionic solution. That's an aqueous ionic solution of NaCl. Now, what you have on the right is you have the molecules for sugar, glucose. Now, the molecules glucose do have a polarity aspect to them, and therefore they dissolve very well in water. But you'll notice the molecule itself does not dissolve, where on the left side, the entire molecule complex dissolves into separate ions. Now, what is the actual dissolving process all about? The answer is that the solute, which in this case, for example, would be the sugar or the salt, and the solvent, which almost always is water, they have a strong attraction to each other. And that attraction is based upon their charges. And the basic rule says that like will dissolve in like. What that means simply is that polar ions will always dissolve in other polar material. So they're able to dissolve with each other based upon the charge. So here you see water, which we were just discussing, is very, very polar, and the oxygen, which is red, that's polar negative, that's on the left side. Notice it will be attracted to the positive sodium ion, and the polar positive side of water on the right is attracted to the negative ion, which is chlorine. Now, what question arises is, notice the purple sodium, which is plus, and the green chlorine, which is minus, they should attract each other. So why don't the Na plus and Cl minus, why don't they stay together when placed in water? And the answer is because the attraction of the water to the ion is greater than the attraction between the two ions themselves. So you see here the attraction of the polar negative water to the sodium positive, that's greater than the attraction of the Na plus to Cl minus, and so the Na plus Cl minus would separate. And here we have, of course, a polar bear in polar water. They clearly do like each other. So what is the act of the dissolving process? And that's referred to as the hydration or solvation. And this is the actual process in which the ion, which would be, for example, Na plus or Cl minus, becomes surrounded by the water molecule, which, as we said, is very, very polar. So what you see on the left side is all the red with the small white attachments. That's water. And the red is the oxygen, and as you can see, oxygen is polar negative. And so what happens is all the polar negative directing waters surround the positive, let's say this is Na plus, and that's the hydration. That's the water surrounding the plus charge of the sodium. Now on the right side you'll see the yellow negative, in this case we'll call it chlorine ion. And you'll notice that the water molecules flip here. What we have now is that the positive side of the water molecule is directed towards the negative portion of the ion itself. Now this has a number of effects. The biggest one is that the positive on the left, let's call that sodium, and the negative on the right, let's call it chlorine, even if they could attract each other over that distance, the water serves as a insulation. They surround it, coat it, and prevent those two ions from creating a attraction to each other because they're surrounded. So we refer to that as a hydration shell. It's very nicely shown here. Pay attention to the idea that water molecule is oriented one direction, meaning that all the polar negative regions are facing the positive sodium. And that in this case, the positive region of the water is facing towards the negative chlorine ion. And notice that there's this shell or a enveloping of the ions. And those ions have difficulty getting access to each other now because they're surrounded by the water. So what you have here is exactly how does dissolving happen. And on the left, you'll notice there are water molecules, polar water molecules, and they become attracted to the oppositely charged ions that make up salt. So what is in green and gray, green and gray, is that's this grain of salt. And that grain of salt is being dissolved by the water, and it does so by the attraction and formation of the hydration shell around it. This is another illustration of how that process actually does work as it pulls apart the salt grain. So now the polar water molecules are going to interact with them. And so what you have here is you have alcohol, and you have a region of the alcohol that's a 2 carbon, but on that 1 carbon you have a OH group, and that OH group will have a polarity to it, and so the overall molecule is polar because that one region is polar, and that one region can now combine with the water molecule, and so the overall molecule is able to dissolve in the water itself. Now, we must realize that like attracts like. Polar attracts polar, nonpolar attracts nonpolar, but the other two, just not happening. So, a new issue arises, which is referred to as saturation. And when you have a saturated solution, it means you have dissolved all the solute that is possible at a given temperature. Nothing more of that type will dissolve in it. And of course, the opposite would be unsaturated, is that you can still add additional material and have it dissolve in there. The third and final one is a bit unusual, is under certain conditions you can actually cheat. You can actually get away with the dissolving process and actually get more material dissolved into the solution than in fact should be possible at that temperature. In this diagram, it illustrates the idea that if you have 100 milliliters of water with 30 grams of salt, it in fact will fully dissolve, and you will get a homogeneous mixture of the two. Down below, if you were to take 40 grams of the NaCl and dissolve it in the 100 mils of water, in fact, not all the salt can dissolve. Now, the reason why that's true is there's just not enough water to surround the ions that make up the salt. And therefore, the ions have access to each other, and they tend to stay together. and you'd have 4 grams dissolved at the bottom. You would have saturated solution in this case because no more can dissolve in it. Now, it's not good enough to be able to say on a hot summer day, I want some lemonade, and to say it's too strong or too weak. In chemistry, we've got to assign numbers to that. We would like to measure what does it mean to have strong lemonade on a summer day or have weak lemonade. In other words, the strong lemonade is concentrated and the weak lemonade is not as concentrated. How can we express that in a measured amount? As you might suspect, it's going to be based upon the solute, which is what got dissolved, and the solvent, which is the liquid it's dissolved in, almost always water. Let's take a look how you do it. We can measure it based upon molarity. You can measure it based upon mass percentage, You can measure it based upon grams per liter, and you can measure it in parts per million. Let's take a look at a few of these calculations. The first one is the molarity, and that is the one that we'll most often use here in the class. The molarity is the moles of a substance based upon 1 liter of solution. So that's an equation you're going to want to know. So molarity is how strong or concentrated a liquid is. And it's the moles of the powder, like salt or sugar, the moles of the solute, divided by the liters of the solution. Notice, this is not just the solvent. In fact, it includes the volume occupied by the powder that you added. The capital M is the symbol for the molarity, or it's moles per liter to the -1, although it's simply the M is the most common. So here's an example. If I have 0.5 molar HCl, what that means is you have 0.5 moles of HCl in 1 liter, which is the same as 0.5 moles of HCl in 1,000 milliliters. Now here's an example of a calculation that you're going to be working with a lot. What is the molarity or concentration of a sodium hydroxide solution that contains 24 grams of NaOH, that's sodium hydroxide, dissolved in 300 milliliters total volume? Notice that includes the volume of the NaOH powder also. So we're asking about molarity. Molarity is moles per liter. We use dimensional analysis, and what we see here is 300 milliliters, which is the number you're given, the volume, times 1,000 milliliters is 1 liter. So you get 0.3 liters. So we now take the 24 grams of NaOH, and that is going to be multiplied times the molar mass of NaOH, which is 1 mole of NaOH. And the answer is this solution is 2 molar. What exactly does that mean? It means that we need to dissolve 24 grams of NaOH in 300 milliliters volume. The concentration of the NaOH of that solution is 2 molar. One rough reference point is 1 molar. Think of it as bleach. Bleach at home is about 1 molar. 2 molar is obviously extremely concentrated. So here now is when you string it all together. 24 grams cancel, moles cancel, all the way through. So Here's another example. A student has 150 milliliters of 2.6 molar lead nitrate. Calculate the moles of Pb present and the molar concentration. So we know that molarity is moles of solute per liter. So here's the first thing we do. We convert the molarity and actually bust out into moles per liter or moles per milliliter. So we extract the molarity or break it out into the actual ratios of moles per milliliter. So what we do now is, if we're given 150 milliliters, we can do a cancellation of the milliliters value. We now know how many moles of lead nitrate we have in the 150 milliliters. Our next move is to take the 0.39 moles of lead nitrate and put it into a volume of a liter. After all, molarity is in a liter value. And we wind up with a 5.2 molar solution of the nitrate itself. So let's go through that again. In Part B allows us to figure out the molarity that we have of the nitrate, and we now take 2.6 molarity of the lead nitrate and convert it then to the actual amount that we would have present in the solution. So besides molarity, we can use mass percent. Mass percent is the mass of the solute divided by the mass of the solution overall. Notice it's the sum of all of them. Equations you want to know. So if we have 31.7 grams of silver nitrate, what is the mass percent? So we start off with the equation, which is mass of solute over mass of solution. We would take our 31.7 grams of silver nitrate divided by the total mass, which is the mass of the water and the silver nitrate, and therefore the mass percentage of silver nitrate is 37.9. The final one is parts per million. This is actually used very commonly in gases, but it's also used in liquid form. So parts per million is the milligrams of solute versus kilograms of solvent. So we've got 1 kilogram is 1,000 grams, which is 1 times 10 to the 6th milligrams. So the Dead Sea, which is near the Middle East, is the saltiest sea in the world. 332 grams of salt per 1,000 grams of water. What's the parts per million? Start with the equation. And the answer is that 332 grams of the solute, 1,000 milligrams is 1 gram. So we're going to convert the solute into milligrams. Then we have 1,000 grams of solvent, that's the water. 1,000 grams is 1 kilogram. So we work the ratio, and it's 332 parts per million. That is another way of measuring concentration. Finally, the density is another method of measuring the concentration of something. This is very common and it's used in breweries, the density indicating the concentration of the alcohol. So 1 milliliter is 1 cubic centimeter. That's the conversion. So there's your units for your density. By definition, water has a density of 1. And that's it. If I could figure out to turn this off.